Hello teachers and welcome to this week's video walkthrough of our latest MathFix. Well, this week's problem looks at the standard 8.G.9, which uses the volume formulas for cones, cylinders, and spheres to solve real-world problems. Well, this problem looks at three-dimensional shapes, one being a sphere, a cylinder, and a cone. These shapes all have equal diameters and volumes. The difference in the shapes comes from what their heights might be. The question is, which one is the tallest? The shapes shown in the problem appear to be equal heights, but can they all be equal and still have the same volumes? In this problem, students can begin to either discussing the shapes in a visual way or jump directly to using the formulas. The visual way might be a skinnier shape or a wider shape or a fatter shape, but the formulas they might use aspects of to look at what supports which one might be taller. There aren't any numbers given in the problem because procedural computations are not the goal of this problem. How can we prove our views of which might be taller without computed value to back us up? Well, if we had equal heights, a cone's volume is only a third of a cylinder's. A cone must therefore be taller than a cylinder to make up for that relationship if we want an equal volume. This picture shows the relationship of how much larger a cylinder is to a cone at equal heights. The height of a sphere is its diameter, which is twice radius. So you can use diameter as the height of the cylinder in the cylinder formula. With equal diameters, a sphere has 2/3 the volume of an equally tall cylinder. This picture shows the larger volume in a cylinder versus that of an equally diametered sphere. In our problem, our volumes are equal and the heights vary. So given all the previous relationships, we see that the shortest will be the cylinder. It carries the most volume for a height. And a sphere carries the next amount of volume for the height and will be the middle shape. The cone, in fact, carries the least amount of volume for a given height, and it will be the tallest in order to make up for that smaller amount of volume for height. Again, we're trying to get shapes that are equal volume, so the heights are what are varying here. This problem can be very valuable to see and think about using some software like GeoGebra or Geometer Sketchpad. This allows students to manipulate shapes while keeping certain traits constant like volume. So those links are included in the bottom of this problem, and you may look at those for use with your students. We welcome feedback on how you and your class engage with this math fix, so please share with us your thoughts, your student conversations, or classroom experiences. And those likes and feedbacks are so valuable, so keep them coming with all that you do within our COP.